Now this is Radio TV Phono Nut, and what we have here is a Silvertone power shifter from about 1940. What this is simply an AC power supply that provides 1.5 volts and 90 volts DC for the operation of tube-type farm and portable radios. Up until the early 1950s, there were many rural areas that didn't have electricity, and there might have been some even later than the early 50s that didn't have it, but we know that at least up until the early 50s there were many rural areas that were not electrified, and such customers needed a battery operated radio so they could be informed and entertained. Well, as the years went by, these rural areas were electrified, and unlike the throwaway generation we have today, the folks back then were not as eager just to throw out an otherwise perfectly good radio, all because they had electricity now and no longer needed a battery-operated radio, so that's where these came in. You could simply plug your battery-operated radio into one of these boogers and plug this into your 110 volt AC outlet and instantly have an AC operated radio. Now I've got 3 or 4 of these things on hand. Every one of them, I believe, were found in the insides of radios that I purchased. Silvertone and powr were the most common ones, and there were several different variations of these. They made one, I believe, that would allow the 6 volt battery operated radios to operate on AC household current. They made one for the radios requiring 2 volts, 90 volts, 135 volts, and a bias voltage. But the most common one that you'll find is this kind right here that provides 1.5 and 90 volts, and you can see the various plugs here that accommodate the various battery cables that you'll run into. This one here is the most common, and I've seen this octal type plug used on some battery operated Zenith radios, and I think all these here are for your portable radios. Alright, let's open it up and see what we got. First, we obviously have the original power cord, and it needs to be replaced, but I like this inline power switch. I will add it to the new power cord. Alright, here's the schematic they were so kind to give us. And as you can see, there's not much to it. For the low voltage, we have a copper sulfide bridge rectifier feeding into just a simple pi-type filter network, filter choke, and 2 capacitors here. And for the high voltage, we have a triode vacuum tube wired as a diode in a half-wave rectifier configuration. Same type of filter circuit, filter choke, and a couple of electrolytic capacitors. This capacitor here is our AC line noise suppression cap. So, there's not much to this. Now, I found that in a lot of applications, such as these battery eliminators and the wireless record players that are low current, they'll often use a triode vacuum tube wired as a diode, and that works okay since the current demand is not that great. I anticipate all we're going to have to do to this is replace the caps, and we might have to replace this rectifier, low voltage rectifier, with a modern silicon bridge rectifier. Now, later versions of these battery eliminators, and they were made well into the 1950s, used a selenium rectifier in place of this tube. I might change the tube out to a silicon diode. We'll just see how things go and what kind of mood I'm in. Now, the disadvantage of this type of power supply is there's no kind of regulation. The output voltage is based strictly on the load placed on the circuit. In fact, if we look on the label here, okay, Okay, you're not wanting to cooperate, so I'll just tell you what it says. It says for farm or portable radios using 4 or 5 1.5 volt tubes. Now, if I were to connect a radio to this using only 2 or 3 tubes, although there weren't that many of those made, but there were some, there wouldn't be enough load placed on the low voltage power supply, and there might be too much filament voltage here, and that would damage the tubes. Now, if I was to use a radio using 6 tubes, that would place too much of a load on the power supply, and there'd be not enough filament voltage. The B plus side, that's not really that critical. And as long as you get between, say, 90 and 110 volts, it's going to work okay, and the current draw on that line is not nearly what the current draw on the filament line is. So what I might do with the filament circuit once we get this up and running is just wire 3 standard silicon diodes in series. That'll add up to about 1.5 volts across the 3 diodes, and just wire that across our filament supply, and that should help keep the voltage at 1.5 volts. That's a crude way of doing it. In another scenario, even if you had this plugged into a 4 or 5 tube radio as specified, and if one or more of the tube filaments burned out, you would still not be placing the correct load on the battery eliminator, and that would still possibly give you more filament voltage, which could damage the remaining tubes. So I'm not going to alter this circuit much, but I'm going to try to make it a little bit safer. Now let's look at the inside. As you can see, it's pretty tight in here. I figure it'll be less tight when these older capacitors are replaced with modern ones. This is the rectifier tube. This here looks like the power transformer. These 2 doodads here look like the filter chokes. And this is one of the filter capacitors. And there's another capacitor sandwiched down in there. And there should be another capacitor somewhere if I can find it. Yeah, I think I see it. Yeah, it's down there at the bottom. And this is our copper sulfide rectifier. So yeah, let's get it down to the bench and tear into this and rebuild it and see if we can get it working again. Alright, I'm about ready to start this, and we'll first make note of where all the insulating paper goes, just in case we need it once we rehab this thing. We probably won't, but just in case, I'll take a note of where everything goes. And when you work on something like this, do it thoughtfully. Just don't go in there willy-nilly and start hacking in stuff here, there, and yonder. Take a good look at the big picture and do it as neatly as you can. Here are the 2 low voltage filters, 15 microfarad at 3 volts. Actually, they've still got a good bit of life left in them. This one's reading 1,000, and that one's reading 460, whatever. So yeah, they do need to be replaced, but they check better than what I thought they would. Now, just for size comparison, 1940, 1500 microfarad 3 volt, 2019, 1500 microfarad 50 volt. You can see how much smaller the capacitors have gotten over the years. I'd hate to think how big this old one would be if it was rated at 50 volts. Don't even know if they had such a thing back then, since pretty much everything was high voltage and low microfarad value. Alright, here's our low voltage filter network. Capacitors mounted on this terminal strip. These 2 are ground connections, and these are our positive connections, and I've sanded the chassis down here, and we're going to solder this terminal strip to the chassis and then connect our terminals here to the appropriate places in the circuit. And I'm going to have to move this capacitor out a little bit to solder this particular terminal to the chassis, but this is about the neatest way I could come up with to do it. in such a tight space we have here. Alright, I was looking, and before we put our low voltage capacitor network here, it might be a good time to change out this high voltage filter, and of course we'll have to unplug the tube to fully get to it, but I might need to slide it out this way, and if our low voltage caps are there, we won't be able to do that. So let's just go ahead and get this taken care of, and then we'll deal with our low voltage capacitors. Okay, here it is, and based on the physical size, it's probably not that big, maybe 10 microfarads at 150 volts the most. Okay, this is a double A at 150 volts, so I wasn't too far off the mark. And again, for size comparison, two 10 microfarad 200 volt caps versus a double 8 microfarad 150 volts, a good bit smaller there. And these old rubber wires are flaky and falling apart, so using them to extend over to a terminal strip is out of the question, but these new caps are small enough that I think I can solder them directly to the terminals in which these wires solder to, and then we'll be in good shape, I hope. Alright, here we are. I have the low voltage filter capacitors mounted to the terminal strip, and the terminal strip soldered to the chassis. And here's one of our high voltage filters here, and the other one is sandwiched down here. Like I said, smaller modern day parts have their advantages. Now all we need to do is replace the power cord and dig this line bypass capacitor out, and then we'll be ready to test it and see where we need to go from there. Alright, I've about got it. New power cord, our noise suppression cap wedged down in here. I had to splice it onto the lead from the original cap because it runs all the way over here. I'm about ready to fire this up and see if it has voltage. Here's our DC, low voltage DC output. Should be 1.5 at least. We're getting 0.2, so I believe our low voltage rectifier is shot. Alright, let's check the high voltage. Now, I know the high voltage is working because I'm measuring the charge bleeding off the cap with it unplugged, so that's working. Now I guess all we need to do is replace this rectifier here. Okay, as far as these copper sulfide rectifiers, or whatever the proper term for them is, I'm not that familiar with them, as in I don't know that as far as the voltage drop across them. With a selenium rectifier, if you replace it with a silicon rectifier, you have to put a resistor in series with it to compensate for the higher voltage that you'll be getting from a silicon rectifier, but I don't know whether we'll have to do that with this or not, so we'll have to be very careful when we replace this and make sure that we don't want to overvolt the tubes and burn them out. Okay, I have the offender disconnected, and I'm getting 2.75 AC off of the power transformer secondary, so that tells me that's okay. Now I got to figure out how to get this out. It's screwed in, but I don't know how we're actually going to get to it, because I don't see any way to get this out of here. But let me get a screwdriver and see if I can go at it at an angle and get this thing out of here. Now, I don't have any bridge rectifier modules, so I just made one using 4 standard 1N4007 diodes. Anode to anode, cathode to cathode, ground, AC goes in these two, DC comes out here. Alright, here we are installed. It looks a little sloppier than it would if I'd have used a rectifier module, but you make do with what you have. Alright, what do we have? Unloaded we have, let's just round that up to 3 volts, which means I'll have to try this with a load, but we might have to put a dropping resistor, or we could do what I said before, just put 3 silicon diodes in series, and that'll clamp it down to 1.5 volts roughly. Here's our 3 diodes in series, gives us 1.6 volts. Wire that across the filament output of the power supply, and that should keep our voltage from going any higher than that. Well, I connected the diodes and it limited the voltage to about 2 volts, and looked like a sloppy mess, more than it already is. So I said, you know what? This thing lasted for 80 years with no kind of shunt diodes across the output, and it probably didn't blow up nothing, so it can continue to go. If you want a solid state regulated power supply, there's plenty of those available too. So this one's going back together. Alright, I'm connected to the battery eliminator and turned on, but I'm not getting nothing but a little static every now and then. This is a 5-tube set, and I'm getting 1.1 volts on the filament and 111 B+. The B+ I'm not worried about, but the filament voltage is low. These battery tubes can be especially fussy, especially the local oscillator, and especially when that tube gets weak. I found that if that filament voltage drops much below 1.5, maybe 1.4, 1.3, the oscillator will stop working and your radio won't work. So we're going to have to go back in this and find out why our voltage is low. I don't know if we have a shorted filter choke or a shorted power transformer winding. It can't be much because there's not much to this thing. Here's a 4-tube battery set. It needs to be restrung. The dial needs to be restrung, but I can still tune it from the back. We're also getting 1.1 volts on it, and I'm hearing static. But no stations. So I think this is just a case of we're not putting out enough filament voltage. The oscillator tube is not running because of insufficient filament voltage, which translates into insufficient emission. So we're going to have to go back into this and get that voltage up. Okay, across the filter choke I'm reading 4.2 ohms. Now I don't know whether that's too low, too high. Can't imagine it being too high, because they don't give you the DC resistance on the schematic. In fact, they really don't give you any values on the schematic. Okay, I disabled the filter choke. I just ran the output, the filament supply, off of the first filter capacitor. Got a lot of hum, which I expected since there's no choke filtering it out, helping filter it out. But our filament voltage only jumped up to 1.3 volts. Radio was trying to play. So I think that tells us the choke's not the problem. The only other thing it could be is the power transformer, for some reason, is not putting out quite enough output voltage. And I don't know how we're going to get around that. Coming up with a transformer won't be a problem, but I might have to mount it outboard on the case somewhere, because there's certainly no room to mount one inside of here. Here's the transformer, and I hadn't even figured out how this is mounted in here. There are no screws or bolts or nothing. I don't know if this is a compression fit or what, but if I could get this out, I could probably find something modern that's small enough to fit in here. And yes, this is just a compression fit. What I'll probably have to do, I think Antique Electronics Supply sells a transformer, but it does not have I think all it has is it has a high voltage winding and one low voltage winding. It does not have a separate 6.3 volt winding for the tube filament, but that's no big deal. I can eliminate the tube filament and go solid state with the high voltage. Alright, I'm getting 2.8 AC unloaded off of the filament winding and 106 AC unloaded off of the high voltage winding. I would think that filament winding should be just a teeny weeny bit more. And if the transformer has a shorted turn, or turn or two, that might be enough to That might be enough to lower our output some. Here's a low voltage transformer that I found in my junk. Excuse my French for saying where it come from, but I'm pretty sure this came out of a Crosley record player. I know that's a dirty word on this family-friendly page, but just thought I'd let you know. Alright, I'm going to power it up and see how much unloaded AC we have coming off of here. 12 volts, which is too high, so we're going to have to use a resistor to lower that, just again strictly for testing purposes. And then we're going to see if we can get our filament voltage using the original filter choke and the original, well, let me rephrase that, using the original filter capacitor network to get our 1.5 or 1.6 volts on the filament line for our radio. Now I will say this is, like so many other projects, turning out to be way more than what I anticipated. I figured new caps and new rectifier and this thing would be ready to go, but sometimes you run into something that is a little bit unforeseen. Now some might ask, well, if the transformer is shorted, it should be smoking and running hot. Well, number one, I didn't leave it plugged in long enough to do any of that, and number two, it might not do that, because if you've only got 2 or 3 shorted turns on the secondary, and since this is such a small transformer, it might not overheat and smoke unless it was plugged in for a very long time. So we just have to go by our voltage readings and whatnot. Okay, I'm running the transformer through the original filter network, and I'm getting 15.8 volts, which is way too much. That would pop some tube filaments in short order. So I'm going to use my resistor box, and we're going to set it to its highest value and plug our radio into it and keep running it down until we get about 1.6 volts, and hope we don't blow any filaments in the process. Okay, we're getting somewhere, but obviously we can't have it like this permanently. I have a 15 ohm resistor connected between the output of the transformer, which is AC, into the input of the bridge rectifier, and with the load of the tubes in place, that gives us about 1.7 volts. I'll turn it on and show you. Hopefully we won't blow up anything. Let that rectifier warm up so the high voltage will come up.
Open borders. You know, it was funny. When I saw this, I think it was Sweet Baby James that first sent it to me, but
as you can hear, the radio is playing just fine, running at 1.7 volts. Now, to illustrate what happens when the filament voltage goes too low, let me jump this up to a, what's the next resistance value on this thing? 22 ohms?
He survives his first dance-off, if you want to call it that, but, you know, if you look back at...
At 1.2, it's still playing, but the volume went down drastically. Let's go up one more notch. And at 0.8, does nothing.
Your fortune, your identity, there's only one way to do it. Cyber criminals, they're after everything you have. Gotta understand this. Now, we may have the most...
cut it off here. Now, yes, it's working, but electrically speaking, there's some problems with this. It's the same problems that this thing had originally. There is no kind of voltage regulation whatsoever. What's coming out of this socket to the filaments is dependent on the load that's placed on the power supply and the incoming AC voltage to the transformer. If our load is not sufficient, it's being placed on the power supply, we could have too little or too much filament voltage, and like I've already stated, too much filament voltage could damage the tubes. And if the line voltage, incoming AC voltage fluctuates too much, that could also cause too little or too much output here, which could cause problems. So, I think what we'd be better off doing is just, despite all this work I've done, putting everything in here nice and neat, I think the best thing to do at this point would be to just gut this, completely gut it, and put all new components in it. In other words, we'll have the vintage look on the outside, but modern technology on the inside. And here's a schematic diagram. I've built something similar to this before. As you can see, we have our power transformer here. And for the low voltage, we go through a bridge rectifier diode and a standard filter capacitor. Then we have an LM317 adjustable voltage regulator and its supporting components. And then just to be on the safe side, we have 3 silicon diodes wired in series on the output. That's supposed to help keep the output voltage limited to around 1.5 volts in case this regulator should short. Okay, so down here we have an optional bias supply that provides C voltage. It's needed for some radios. We won't need this for this application. And then moving down here we have our B plus supply, which is simply just a bridge rectifier diode network and a 100 microfarad filter capacitor and a string of Zener diodes. And if you needed to, you could tap off of each Zener diode to get your desired voltages, because some radios require either less than 90 volts B plus or they require multiple B plus voltages. But in our application, all we'll be interested in is the 90 volt supply. And as far as a transformer, that's going to be the most expensive part. We're probably looking at about $30. Now what I could do, if there's enough room in the case, and if I can find another one of these Crosley transformers, I could wire 2 of them back to back and then take our low voltage off of the junction where the 2 are wired together, and then take the high voltage off of the second transformer output, and wiring them back to back like that will give us isolation. So I think that's what we're going to do, but this video has already gone on longer than it should have, so I think we're going to end it now. We'll call this part 1, and when I procure the needed parts to do this, we'll get back on here and strip this out, mount everything in here, and hopefully we'll have a nice little vintage looking battery eliminator with all the modern electronic conveniences on the inside. Once I get rid of the original power transformer and the filter chokes and everything else, there should be plenty enough room to do what needs to be done here. Well, as luck would have it, I found another identical transformer to the first one, so yeah, we can wire these back to back, put them in the case, and there should still be plenty enough room for all of the additional components that are needed. Yes, we can mount those to the rear of the case. They should fit in there and still have enough room to put the top on. And once we get everything else out, there will still be enough room for the extra components. So we'll call it a day with this video, and as soon as I get my hands on the other components that we need, then we'll continue this. There will be a part 2.